Hey everybody, this is Larry. This is day 18th of the June Leetcode Daily Challenge. Hit the like button, hit the subscribe button, join me on Discord, you know the deal. But anyway, today's problem is the range sum query. Friday is here. Happy Friday, Friday fun day. Friday? Anyway, I am solving these live, so I am very incoherent. So if you need to fast forward or whatever, you should do that. Because it is going to be live. So, okay. Today's problem is range sum query mutable. So the key thing is that update the value, calculate sum element between left and right. Okay. This is one of my what is n? N is 3 times. This is one of my numbers is from that to that. But yeah, this is basically prefix sum kind of in a way, but in a binary index tree kind of way. There are other ways to do it as well, but that's the way that I usually do it. I mean, or segment tree, I suppose, but one of these high power things. Yeah. Yeah. I mean, I don't. There probably are different ways to do this, possibly, but that's the way that I've always done it. And binary index tree is kind of this high powered thing that. Yeah, I'm trying to think. I mean, right now I'm just trying to think whether there's another recommendation, but this really is tailor made for that. If this was static, then you would just do something with prefix sum. And in this case, because it's mutable, you have to update it, and for that reason, a binary index tree is where you want to go. Yeah. I don't know how. Yeah, I mean, there's some bookkeeping and stuff like that, but I think that's the way to do it. I'm not gonna lie, the thing with binary index tree is such that it doesn't really come up that much on interviews, or at least it shouldn't. If that's a new thing, then correct me in the comments below. But there are other ways to do it. Of course, you can effectively also. You can do a manual binary tree where you just kind of split the left and the right of the domain, and then kind of give them that. Of course, that is essentially a segment tree as well. Sorry, I mean, I know. I just don't know how to go about this. The thing that I would say is that I don't think I'm going to spend that much time going over the binary index tree, just because it is. I don't think it's really worth people's time to go over binary index tree. I think if you, like, to be frank, if you are on an interview or just whatever session where you need the binary index tree, it's probably like, unless you feel like you're really solid, you can solve every hard or whatever, or most hards, then maybe that's where I would play around with, or enough hards. I think that this is not really within the scope of most interviews, but maybe I'm wrong there. So leave a comment about that. For that, let's see if I could pull up a link. To be honest, I would just go on Wikipedia and look it up. This is the article that I would recommend. It's literally Wikipedia article, binary index tree, and it's a Fenwick tree as well. I forgot about that part about it. But the key part about this is that it has prefix sum, but doing it in a binary way. I don't usually write it quite this way, to be honest. And this is one of the few things that I do have. I do have a template for, but you should use your own template, because part of it is going to be understanding. But I'm not going to even use that here, but the thing is about binary index tree is that it is it is an abstract data type. And what I mean by that is that in theory, you should be able to plug it into something and use it without any reservation. So that's basically the idea that I'm going to use. And I'm going to just implement the tree here. I have to double check to make sure that is right, because it's not something that I do often, and it's something that I've only learned the last couple of years. So it's not, but it's still as an abstract data type. It's something that you can plug and play into other things. So okay, so let's do bit. I think you have a max n, say. So yeah, solve that. Maybe n might plus one. Maybe, I mean, I don't think this matters that much unless you're really nuanced about it. What we would do is just make it a little bit bigger anyway, because this n is not the number of elements. Well, it can be depending on what you do, but actually in this case it is the number of elements, but you can just make it a little bit bigger to go over it, right? So yeah. And then I just remember there's two key functions. One is increase, and it is just basically the index, and then the value that you're indexing, you're increasing by, right? So then here, and as I mentioned again, this assumes that you have some learning of binary index tree. Maybe I'll do a separate video in the future, but I'm not going to make that the focus of this video, because it is something that, to be frank, I understand it as an abstract data type, as I keep saying that, meaning that I know how to use it. But to be honest, I can explain it in a rough way, but I think I have to prepare for it a little bit, and I don't think it's going to be that coherent without that preparation. It's not something that I know so well that I can explain, to be frank. So that's my disclosure. But you have the tools, so I believe in you. And maybe people can, leave a comment below on what they think about it. But yeah, so index is equal to whoops, this is this index. So yeah, so while index is less than sub.n, index 1. And this part is kind of confusing, I'm not gonna lie. Let's call this delta. Oops. Because this part of the binary index tree is very I think it's probably the more confusing part to understand. But you can think about the way that I would think about it, and there are visualizations, but I'm just giving you a 2-second overview, which is probably not going to be fair. So if you don't understand it, it's probably my fault, not your fault. But basically, you try to think about each index. Of course, it's a binary number, but that binary number representing a tree, and that tree, having a path, and this kind of gets us to, go down that tree. Again, like I said, it is a little bit hand wavy, so I don't blame you for saying that. But again, the way that I want to think about it, or want to demonstrate to you, is that now that I have this binary index tree implemented, and this is pretty standard binary index tree. Maybe there are other ways of implementing it, but still, either way, is the binary index tree, which just like prefix sum has two functions. One is the increase function, so you can think about it as an interface, right? To where the implementation doesn't matter. I mean, I know that it matters, but in terms of solving problems. But I want you to think, or I want you to see how I think about it. Maybe you can do it at a different way when you do it. But basically, the idea is that you have this abstract data type, that exposes two functions. One is the increase function, and one is the sum function. And the increase function, of course, while I'm doing that, let me document it. Increase the element at index by delta, right? And sum gets the total of the first index indices or elements, right? And that's basically the idea. While index is greater than or less than 0, total solve that elements of how did I mistypo that badly? And then index. Oh, whoops. Again, there are other ways of writing it, so you might see it in another way, but it's equivalent, I promise. Or if not, then I have a typo, but conceptually it is equivalent. And then now we can have a, so this is basically the interface behind it, and all you have to know about this, for me anyway, is that both of these are log n. And you can kind of look through the code and you could kind of see this, because this will add a bit every time, and it will go there in log n time, and here it will also loses a bit every time, so it will get doing log n time. But I'm going to add one more thing, which is sum by range. It's just a helper function, no big deal. And this is, of course, just return self.sum of left minus 1. Something like that, right? And this kind of makes sense. The way that I would think about this, and of course this is all of log n, and of course this is just some gets the total between the indices left and right? I mean, I think this one, that one makes sense. The way that I always talk about prefix sum, and this does require prefix sum as a prereq, is that sum of left minus 1 is just a sub 1 plus a sub 2, or maybe a sub 0, plus dot dot dot, all the way to plus a of left minus 1, and then a sub, the sum of right, of course, is the same thing, except for that goes plus a sub left plus dot 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 plus a sub right. Oops. So then the subtraction of these two will give you this chunk, which is extra, right? So that's basically the idea about arranged prefix sum query, right? So that's basically the idea. Again, I apologize if this isn't a good understanding of binary index tree. This is maybe intentional. I might do a video just on this in the future, so that we can go over it more in detail. But for now, it is beyond the scope because it would take too long, and I'm not even that prepared for it, to be frank. It's one of the few topics that that's the case, but which is why I would never ask a question like this on an interview, because it is just not that useful for that reason. Though maybe there's some hacks and I forget about them. But this is the canonical, or one of the canonical ways of solving it. So maybe there's some hacks you can do to do it, but that's going to be more sketch. And also, of course, this is segment tree, which has the same logic, but it's easier to explain, to be honest, but also way beyond the scope of interviews, if you ask me, but that's besides the point. Again, this is, if you were to Google binary index tree or Fenwick tree. And okay, so now given this, and let's pretend I just copy and paste, or I actually know this, roughly speaking. Sometimes I have a typo, but roughly speaking, I do know this. So yeah, but essentially, this is one of the few things that I just regurgitate and copy and paste. But let's say you have this as a library function somewhere. Then what do you do, right? Then the question is about using it. And note that this is, like I said, this is a standard binary index tree with the sum. You can actually build the solution into this, but for the purpose of me thinking through this problem, I'm not going to do that. I'm going to, just thinking about, okay, now we have this tool, what can we do, right? So now we have, what is the n in this problem? Oh, I guess they just give you an entire array. Huh, okay. Okay. It just give you an entire array. So n is equal to length of nums. Maybe a couple of ways doing it. But it doesn't really matter because it's the same thing, right? So we have just for x in nums, we just use, oh, I have to set up the tree, of course. Self dot bit, notorious bit is equal to bit of, I have to give it an n, right? Or the way that I did it, I have to give it an n. You can actually, the cool thing about this is, and I didn't realize this until I saw it on a contest maybe a year ago, maybe less than a year ago, is that this actually, I used an array to implement this, but you can actually replace this with a dictionary and it'll be fine, which is kind of cool. I mean, you use way more space, but probably like 2x space at most, so it's actually pretty sufficient enough. Anyway, so yeah, so now you just do that increase index and x. Of course, I have to do enumerate because I forgot, just for the index. And then that's basically how I do the initialization, and then update. So note that my interface has an increase function and not an update function. So then now we just have to keep track of it. That's not that bad. And then we just get the delta back out of the delta. So yeah, let's do that. Self.nums is equal to nums. Let's just say delta is equal to self.num sub index minus value, or maybe the other way, because we want to get it to value. So okay, yeah, I think it's this actually. And then you do self dot bit dot increase self dot index and then delta, right? So that's pretty straightforward. So okay, so now sum of range, of course, this is literally our like we have a function for this actually, and this should be good, minus some typos and bad implementation, which I am been kind of bad about it recently. But oh, I forgot to pass an n. I set up n and then I forgot to actually pass it in. But yeah, I spent a bit of time kind of typing this in, but as you can see, after I have that typed in, like I said, this is so tailor-made that I have 5 lines of code, give or take, after that, right? And of course, I have to fix some typos, as I said. So yeah, so that looks good. Let's give it a submit. Ooh, yikes. How did I get that wrong? Maybe I have an off by 1. Been really sloppy lately, so but let's see. Okay, I mean, I already knew that, but why is that wrong? Dun dun dun. Did I do the update thing? Did I get the indexes wrong? No, seems okay. Okay. Then what am I doing? Okay, let's go through it. Sum of range from 3 to 8. Nope. Sum of the range from 4 to 4. Yep. 4 to 4 is going to be a 6. Okay. Update from 0 to 4. Sum of range from 0 to 3 is... Why do I have this wrong? Dun dun dun. That's yikes. Yeah, because the last number is 1. Why am I off by such weird amounts? Last number isn't... Oh, I am dumb. I knew... Oh, I meant to do this, but I forgot to... okay. Yeah, that was just sloppy. Yep, okay. But like I said, maybe I spent too long talking about bit that I forgot about this. I was thinking about it as I was writing it, but I think recently I've been really bad in the sense that because I'm explaining stuff, I forget stuff right after I explain them on the video. I need to focus on just implementation maybe because yeah, as soon as after I talked about this, I forgot about this line even though I knew that I had to do it. So let's give it a submit. Hopefully this is right this time. Okay, yeah, so that's good. Like I said, right? So now, let's live in a world where you pretend you already knew how to do binary index tree and stuff like that. This is like 5 lines of code, right? So the core part of the problem is in the binary index tree, which kind of make this a crappy problem for an interview because it's either they know it or they don't. No one is coming up with binary index tree or segment trees off their head. So if they know it, then they'll get it. If they don't know it, they don't get it, right? So that's why I wouldn't ask this. But let's see. Maybe I'm missing an obvious solution. Let's click on solution to see. Real quick, and then we'll go back for naive. Obviously, it's going to be too slow. Square root decomposition is even worse. Maybe I could explain that one. Segment tree. We talked about segment tree vaguely, and then yeah, binary index tree as well. Square root decomposition I could talk about, but I'm not going to. It's a little bit. It's fun actually, but maybe another time because that's some advanced topics. So this one, like I said from the beginning, I don't think I missed anything. So except for having this line, I guess I missed that. But yeah, so if you have binary index tree knowledge and you want to go learn it, that's fine, that's fun. But I would, as a strategy, like it's not worth knowing until much later because, like would I rather be really solid in tree problems, like regular tree problems, because that gets asked more. Why be more solid at dynamic programming before learning this? The answer is yes, for the most part. I don't see it being asked, at least in the USA, for interviews, or at least like if you do, that's like the less than 1% chance that why are you studying for those possible things. I would just get better at other stuff. Yeah, that's what I have for this one. Oh yeah, let's go over the complexity real quick. I hope this is very straightforward though, because as we said, increases log n, so the initialization is going to be n log n. In this case, update is going to this is log n, and the other stuff is all of 1, so this is a log n operation. And sum of range, as we already talked about, is log n, so this is also going to be log n. Like I said, everything is very tailor-made for binary index tree or segment tree. So yeah, and I don't think it's worth going over square root decomposition either. I think though that one is it's easier to explain, but I don't want to do it this time. Let me know what you think about it, this problem. Let me leave a note in the comments if you want me to go do a binary index tree video and explanation and so forth. Just let me know what you think. I personally, I let you know what I thought, which is that this is a silly interview problem, and I don't know if there's anything. I mean, I thought maybe I missed a silly solution, but I mean, there's a naive solution, but it's going to take too long, right? For 30,000. So yeah, that's all I have for this one. Let me know what you think again. Happy Friday. Have a good weekend. Stay good. And yeah, and happy Father's Day soon. I mean, I guess I would say it again. For y'all fathers out there, or your father or whatever, stay good, stay cool, and I'll see you tomorrow. Bye bye.